All right, so welcome back. I'm very happy to say that we have Eve Ostriker, who got her degree at UC Berkeley and has been faculty at University of Maryland and is now at Princeton University. And I think it's that we were very happy to have her give this lecture because she is has been in the forefront in connecting galaxy properties and interstellar medium properties using computational methods. So she's going to tell us, give it a first of a series of lectures on the interstellar medium.
Thank you. Okay, am I audible? Good. Great, so it's really a pleasure to be here. To see all the students eager to learn about galaxy formation and the senior people who are so eager to teach them and learn from them. So this is going to be a really exciting several weeks for, I think, all of us. And thanks to all of the organizers for making this possible. So my subject today is, this is the first of 3 lectures. They will be about the interstellar medium in the sense that the interstellar medium is where everything interesting happens. But that includes different aspects. And this first lecture will really be about the interstellar medium itself. And my goal here is to give you an overview, because I think some of the students here are from physics departments. Some of them may have had an ISM lecture that had a somewhat different focus. So I wanted to get everyone really at least on the same page with a broad overview of what is actually in the interstellar medium, how do we know about it, what are the kind of key physical processes. So, and I wanted to start with just this image because it actually shows a lot of what I'll be talking about for in my 3 lectures this week. So this is a resolved image of a typical nearby spiral star-forming galaxy. And you can see, so here are, you can see these star-forming regions here in pink. So those are in pink because you're seeing them in the emission from ionized gas. And that gas is ionized, of course, by the newly formed luminous massive stars. So you're seeing here, this image is kind of emphasizing the interstellar medium. And in addition to that, so that those red regions are actually relatively somewhat reduced density ionized gas. So in addition to that, you can see what's in dark here in either of these images, but this dark stuff. So all of that dark stuff is dust. So what you're seeing is the background light being blocked by dust. And of course, all of the stars, not just these young stars, but all stars throughout time have formed out of the interstellar medium. So the fact that we have an interesting universe with interesting things in it is all, we can say the interstellar medium is what makes this happen. So this is really, I call the interstellar medium the engine of cosmic evolution, because this is, both where the gas turns into stars and where the return of energy from stars to and metals as well, where that return to their surroundings is really what makes the cosmos evolve. It would be really boring if there were no interstellar medium. Stars help. I have to admit that stars help. They do their part. Okay, so to really understand galaxy formation, galaxy evolution physically, to understand the physics, you have to understand what's going on in the interstellar medium. So it's not just a black box that you're turning parameters. There's actually physics happening here. We're all physicists, so we're interested in this by definition. And so I'll be focusing on the ISM in this first lecture. But just another, just to say where we're going, I'll be talking about, in my second lecture, I'll be talking about these, how the star formation actually takes place within the dense gas, so these star-forming regions in the dense gas. And also, I'll be talking about in my third lecture, the feedback from star formation. That is, how does the energy return to the surrounding ISM? And the aspect of it you see most clearly here is, of course, the radiation feedback, but you can indirectly see some other aspects in the sense that this material is not at all smooth. So part of the reason it's not smooth is because there have been supernovae, and those supernova explosions basically move all of that gas around and create turbulence, and so you can indirectly see those effects as well. And I should say, also, please stop me at any time because I think I would be exhausted if I talked for an hour and a half straight with no breaks for interesting questions. Okay, so this first lecture is what's in yellow here about the interstellar medium. So, what terms will you hear in discussing the interstellar medium? Of course, it's a very because so much physics is happening, it's very complex, and the observed state of the ISM is really due to the interaction of very many different physical processes. And the terminology you'll hear is you'll hear about phases of the interstellar medium. Well, phases can mean there's kind of two different aspects of phases. One is chemical phases, so the gas can be molecular, atomic. Can people see my pointer here? Okay, so I think that's easier than trying to use the stick. So there's molecular, atomic, and ionized gas, so those are the different chemical phases. There are also different thermal phases, so there's cold, warm, and hot. And then you can sort of take a cross product of those, and that gives you chemical and thermal components. So I've listed here some acronyms you'll hear in relationship to what those components are. So the CNM, cold neutral medium, consists of both atomic gas, which is H1. Ramil talked about this already. And I'll talk about diagnostics of each of these components, but just let me first lay out what they all are. So there's the CNM, which has atomic gas, and also molecular gas. That molecular gas is, and I think it's great if you want to take pictures, but I think we're going to have the PDFs available, so you don't feel like you have to take a picture of everything, although it's very flattering. I spend so much time on these lectures. So take as many pictures as you want. So there's molecular gas, which is both, we talk about diffuse molecular gas, diffuse clouds, and also dark clouds and giant molecular clouds. So those are just kind of observational terminology. They're all molecular, but it's a different aspect, really having to do with how they are identified and observed. The giant ones, as you might expect, are much bigger and more massive. And the dark ones are ones that you can't see through in the optical. The diffuse ones are just lower density molecular gas. So then there is the WNM, that's the warm neutral medium. It is what it sounds like. Then there's the warm ionized medium, and that has there's two different aspects of that. There's the warm ionized medium, which is distinctly in H2 region, so that's those kind of pink patches you saw in M83. And then there's the diffuse ionized gas, which is really, it's much more diffuse, as it sounds. It's particularly found at high altitudes. High altitudes. So all of this gas is primarily ionized by stars, we believe. But there's the immediate H2 regions, and then there's the more diffuse ionized gas. And finally, there's the hot ionized medium, HIM. Okay. So of these phases, the neutral phases are the most important for star formation because that's the direct precursor, and because most of the mass is in the neutral phases, that is the atomic and molecular gas, and whereas the warmer phases are really telling us about the feedback that stars and other, mainly stars, the feedback processes, because the energy in those warmer and hotter phases comes from stars. So they really provide direct signatures of the effects of star formation. Okay, so here I'm giving you kind of for reference some typical properties of ISM gas. And if you go different places in a galaxy, it won't always be this. So this is kind of based on the solar neighborhood. So there's atomic cold neutral medium clouds in the solar neighborhood. And I mean that loosely. So this is kind of what you can see from the solar neighborhood. So the typical temperatures are in the range of about 100 Kelvin, so this is quite cold. I also wrote down here the corresponding sound speed, which is about 1 kilometer a second, and typical density of about a few tens of particles per cubic centimeter. So these cold clouds tend to be organized in structures. They're not, the theorist's picture is this round cloud. They're not round clouds. Like everything else, they are kind of filamentary, but some of those observed filaments may actually be sort of ribbons or sheets that are seen brighter when they're more edge-on, so it may look more like a filament. And the same is true for the structure of the molecular gas, that is, it's kind of clumpy, filamentary material. The molecular gas, this is the other part of the CNM. Sometimes people use the word CNM just for the atomic gas. Other times they incorporate the molecular material within this. But the temperature of the molecular gas is generally lower. Although there can be molecular material at higher temperature. Generally, that's shock excited rather than, so it's heated by shocks. But most of the molecular gas is at these very low temperatures. And the corresponding sound speed is, again, quite low. So that's about a few tenths of a kilometer a second. The densities in the molecular material tend to be higher. And when do you get molecular gas? Well, to get molecular gas, you have to be shielded from the dissociating UV, because UV photons will come in and try to dissociate the molecule. So you only have, kind of definitionally, the molecular regions have column densities that are enough to keep the dissociating photons out. Okay, so of the molecular gas, the more massive clouds can be self-gravitating. But molecular gas does not have to be self-gravitating. A lot of it is, but it doesn't have to be. Just to note that the turbulence is important everywhere in the interstellar medium, but especially in the molecular component, because if you look at the actual measured velocity dispersions from the line width, that's a few kilometers a second typically, and you compare to the sound speed of 0.2 of a kilometer a second. So immediately you see that these are hypersonic motions. So with hypersonic motions, you expect turbulence to develop because the viscosity is very low. So we think of these as turbulent structures. So then there's the atomic gas, the warm gas. So this has temperatures of several thousand degrees up to about 10,000 degrees. Lower densities, you'll notice that if you multiply the temperature times the density of the CNM and the temperature times the density of the WNM, that's kind of comparable. So that's rough pressure equilibrium between these phases. The molecular gas can be at higher pressure because it's self-gravitating. And this fills a lot of the volume, maybe half of the volume, near the galactic midplane for our solar neighborhood. That can be different in different regions. So then there's the diffuse ionized medium. It's a bit warmer. It has lower density, largely because it tends to be found at higher altitude, where the overall density is lower. Sometimes you'll hear this referred to as the Reynolds layer, because that's after the person who first identified it in H-alpha observations. Then the H2 regions, those are actually they can have a range of temperatures depending on the average spectrum of the high mass stars that are actually heating them. So for more luminous stars, a harder spectrum, the temperature will be higher. And these also have much higher densities because you've basically you've turned on some luminous stars in what was a dense molecular cloud, so they have higher, you have the density that was high enough to form stars. You suddenly illuminate it with ionizing radiation. Of course, the pressure will be initially very high. These regions expand, but the density can be quite high. So then there's the hot medium. Typical temperature is of order 1 million degrees, and densities are quite low because these were very high pressure regions, so they expanded, and then the remnant gas is still hot, but these are quite low density. And this kind of structure or morphology of these, so this hot gas is found either in individual supernova remnants or in superbubbles or kind of chimneys that are emerging from galaxies. Yes?
As you Here, there's also this Lockman layer, which is the same but in neutral hydrogen. So
Yes, yes.
I was wondering, is there a reason for which you have not included that, or you think it
Because
is part of the...
so that is the atomic, I mean, I included that as atomic gas, which it can be at any height. So, yeah. Yeah, so that's, so you can have, I don't know whether, maybe I'll talk about this later, but fountain flows are basically driven by feedback by supernovae, and so gas can be travel up to several kiloparsecs and rain back down. Some of that will have paths to hot stars, which can ionize it. Some of that gas will not, and so it can be either neutral or ionized. Of course, material that's raining into the galaxy can also be either neutral or ionized, depending on what radiation field it sees. So both of those, but can be, you can have high altitude atomic or molecular gas. Thanks. Okay, and just a note here, and I'll come back to this point later, but the temperatures are basically set by microphysics. That is, what are the transitions that provide cooling in gas? That microphysics determines why there are particular temperatures of the interstellar gas, whereas the densities, so this is relatively, there are variations, but that's relatively insensitive to location, whereas densities depend a lot on where you are because something is changing, and that something is the pressure is changing, but that change in the pressure really has more to do with a change in the density than a change in the temperature, because the microphysics says this is this is where we can get to from these transitions that are available. Okay, so how is this gas distributed in galaxies? Of course, it varies a lot from galaxy to galaxy. This is for the Milky Way, which is kind of typical in the sense that the neutral gas is mainly, the neutral gas is the dominant part, that is the atomic and molecular. This is mostly molecular in the inner parts and mostly atomic in the outer parts. So this shows a profile of the surface density of molecular gas. This is from Higher-Dame's review article, going from, it's higher in the inner part, and this is what you see here, this so-called molecular ring, which may also be molecular spiral arms. We don't really have good positional information about where this is. So this is highest in the inner parts, and then it drops off in the outer regions. That's the same for the other disk galaxies. Over here, this shows the surface density either in solar masses per square parsec or particles per square centimeter of the atomic gas. This is also higher in the inner regions, but the atomic gas generally saturates at about 10 solar masses per square parsec, because that's where you get to a high enough AV that then kind of the average conditions tend to shield gas, and preferentially you can get molecules at high surface densities. So that's what the kind of radial profiles look like in some galaxies. So you can see that this is extending out to 20 kiloparsecs. Some galaxies, the atomic gas extends even further. And then this just shows what the volume density looks like. So the volume density, of course, there's assumptions that go into computing volume density profiles, but this is just showing you that the volume density is very low at large distances and increases towards the interior. Okay, so what about this is another view of molecular gas. And one thing you can see in this view is you can see, the molecular gas is bright in the center here, so that's this inner molecular ring. But there's also a lot of other things like this. So what are these things? These are actually individual molecular clouds that are closer to us, kind of solar neighborhood molecular clouds. And this band here shown in red is what's known as the Gould belt. So you'll hear, that's a term you may hear, the Gould belt. And those are, so there are a number of molecular clouds in this Gould belt that have names that you might hear. So over here is the Taurus Perseus Auriga complex. Up here, there's the Polaris flare cloud, Cepheus. Let's see, I guess what else? There's some others that I'll show you later. There's Aquila here, Over here is Orion. So these are clouds that are, since they are more in the solar neighborhood, they're relatively quite well studied. And I'll come back to these clouds when I talk about star formation. So when you look at this, kind of gives you an idea of why it's actually pretty hard to be an observer, which I'm not, of the interstellar medium, because you don't know where anything is. You're seeing this superposition of everything just on the sky. You're seeing, this is just brightness temperature. So the brightness is things that are closer, are taking up a larger solid angle, but these are just individual clouds. And so you have this, everything is sort of laid out in front of you in a kind of confusing way. So that makes it difficult. That's one of the inherent difficulties of studying the interstellar medium in our own galaxy. but this is, I think, something that with the advent of Gaia, where we'll actually be able to get better distances to clouds from foreground and background, distances to foreground and background stars, this will actually be a great aid in ISM research. And this actually is a better view of a number of these clouds. So these nearby clouds, and I'll talk more about these when in my star formation lecture, my second lecture. But this is just to kind of give you, a little picture of them and this is as seen in dust emission. So this is the Taurus cloud, the Ophiuchus cloud, and Orion. That's Orion A and Orion B. So these are all similar in angular size on the cloud on the sky. You can see that they're all about 2 degrees on the sky if you actually read the scale here. I did not adjust the size to make them precisely the right angular size, but I did try to make approximately similar. So they're all similar angular size. Orion is about an order of magnitude greater than mass, so it's further away than so it's about 500 parsecs away compared to about 100 parsecs for these other nearby clouds. So this, it may not look much different, but in this view, but it's much more massive. It has about 10 times more mass, and it's actually forming high mass stars, which these other clouds, nearby clouds, are not. So this is a view of Orion. So here's a view of Orion. So for us theorists, it's kind of nice because you can recognize that constellation. That's one that you can actually know and remember, at least for me. And in particular, these are regions of high mass star formation. Right here, the Orion Nebula, and then the Horsehead Nebula. So those are right in Orion's sword and Orion's belt. And this is the kind of this region. What's shown in the big picture here is the part of the Orion A molecular cloud. So this is from very recent survey so this is a survey of a single cloud, Kong et al. From this year. And Orion is very well studied because it is a prototype. It's our best prototype for star formation in our galaxy. It's relatively nearby. It forms stars of all masses. We see both massive stars and low mass stars. And so it's an extremely important prototype. It's gotten a lot of attention. Right here is, this is just a selection of the studies of Orion and over the years. So this goes back to, I can't read how far it goes back to, 87, I think. So this was the first survey, the Bell Labs survey of, which was a high resolution survey of Orion. And then up to this present survey, which was Karma and NRO. So Karma is an array, NRO is a single dish, which you need to fill in the UV plane. So this paper is Kong plus 40 co-authors. This is obviously, there's a lot of interest in this. So this kind of, and just so that you know, what's shown here is total intensity, and what's shown here is a velocity map, so it's colored by velocity. And so what we, when we say that clouds are turbulent, it's because we have velocity information about them, this detailed velocity. And this is, I think the resolution is, a fraction of a parsec. I thought I wrote it down. And the velocity resolution is also very high. So I think maybe that's, I don't remember the number, sorry, but it's very high resolution. So in addition to our own view, our view of our own galaxy in the interstellar medium, one of the things in the last decade that's been very exciting is higher resolution observations of the ISM in external galaxies. And here are some examples from some of the studies. This is of atomic gas. This is of molecular gas in external galaxies. So at this point, there are some surveys that have some tens of galaxies that have been surveyed at about kiloparsec scale in atomic and molecular gas. Not all, it's actually, as Ramil mentioned, it's harder to do the atomic, both because of the resolution. The 21 centimeter is bigger, so you have proportionally less good resolution inherently. Also because 21 centimeter is fainter, so that also makes it more difficult. But we have of order some tens of galaxies observed at kiloparsec resolution in atomic and molecular gas. And now these surveys are increasing to larger numbers. This is about 100 galaxies observed in molecular gas in the EDGE survey. And what is very new and happening now is we're going to even higher resolution, at least for the molecular gas. So this is one of the first papers from the FANGS. FANGS is a kind of collaboration that does surveys. So it stands for Physics at High Angular Resolution in Nearby Galaxies. So this is from one of their papers on, this is a survey. This is actually, I can't remember how many galaxies. This is a sample from the first survey of molecular gas in spiral galaxies. It will ultimately go up to 80 galaxies, mapping at angular resolution of an arcsecond, which in nearby galaxies gives you a resolution of better than at this, so it's even better than 120 parsecs. It kind of goes down to 40 to 60 parsecs in these galaxies. So that is kind of amazing because that's the same scale as molecular clouds in our own galaxy. So we'll really get a much higher resolution picture than has been possible before. And one of the things about that is that, since you can see these regions individually, you can map them on the galaxy, then there's not this distance ambiguity that we have in our own galaxy. Okay, so back to the Milky Way. So I love this picture because it shows all of the ISM and more. So laid out for you, this is, of course, a panoramic picture. And you can see the phases that I talked about, the atomic gas, the molecular gas. You can see the hot gas here in X-rays. The other thing that I haven't really talked about in detail yet is you can see that what's dark here, again, is the dust blocking the background optical light. And then you can see in the, this is stars that is visible in the near infrared. Here in the mid-infrared and the infrared, that is emission from the dust. So dust is very important. Here's a Planck view of the dust. So you can see it's concentrated at the midplane because the gas is concentrated at the midplane. But in this projection, of course, we can see also above us, and so this is a full 4 pi. So we can see that the density is dropping off at high altitude, but there's dust everywhere, just like there's gas everywhere. So how do we know about what the properties of the dust are? Is properties? I don't know. Dust properties. So first of all, we infer the presence of dust from the emission in infrared and submillimeter, and that's what's shown here. This is so over here in the in submillimeter, we're essentially seeing a very good thermal spectrum. I think this is 18 degrees, so very nice thermal spectrum from the dust. So then at shorter wavelengths, things get a bit crazy. And the reason things are getting a bit crazy is that you're essentially seeing emission from very small particles where photons that come in, they don't just get absorbed and then re-emit, as a black body. They are sort of emitting in a way that reflects their internal molecular structure. So for these very small grains, the fact that the emission the spectrum looks really weird here says you're doing solid state physics with a telescope. So this is from grains that are small enough, that is less than 100 angstroms or so, that absorbing a single photon, changes the internal energy levels of this big molecule in wacky ways, so that when it emits, it's reflecting the internal structure of that big molecule. So that's why there are all these features in the infrared. So what we know, the emission can be interpreted, and absorption as well, I'll get to that in a minute, as being consistent with the population of grains which are a combination of silicates and carbonaceous grains. And this shows the Weingartner and Drain model of Milky Way dust. This is the relative number as a function of grain size. So this is a model. We haven't gone at it to scoop up the dust, but this is the best dust model that you can make based on the observed constraints, where the grain sizes are generally submicron. So this is going from 10 to the minus 3 up to a fraction of a micron. Most of the mass is in the large grains. Most of the area is in the small grains. And the total mass of the dust is about 1% of the gas mass. So we also know about dust from extinction. So when you look through, the ISM at stars, then you know what the spectrum should look like, and so then there's the observed spectrum is changed by going through dust. And so so what's shown here are actually one parameter family of curves which are related to the extinction. And RV is a measure, so this is the extinction at V divided by the extinction at B minus V. So that's telling you something about the properties of grains. And first of all, the total extinction is decreasing at longer wavelengths. So this direction over here is towards the IR, towards longer wavelengths. That's telling you, the fact that extinction is decreasing is telling you that grains must be quite small wavelengths. So that's why we know they're submicron, because if you just had a boulder, if you had boulders, then, if you've shown an optical flashlight or a UV flashlight or a millimeter flashlight at a boulder, that light would all be extincted the same way. So the fact that there's differential extinction at different wavelengths means that the grains are quite small. They're smaller than than all of these wavelengths. And there are certain particular features like this UV bump, which suggests that there are carbonaceous grains present. So that is, graphite grains are what leads to this UV bump. So if you look at this in detail, you can see that if you kind of follow these curves, the curves at larger RV here, the larger RV here has more extinction in the IR and less in the UV. So that's interpreted as being associated with larger grains, which suggests that grains, preferentially you see this in dense clouds, a larger RV. So that's associated with grain growth. And then one other particular thing to mention is that the fact that there are specific absorption features seen at certain wavelengths suggests that there are also silicate grains, not just carbonaceous grains. So there's both coal and quartz. So you can, your cosmic beach as well as the cosmic fireplace. Okay, so moving on. So in addition to these material things, there's also, magnetic fields are sort of immaterial, but tremendously important. So how do we know that the cosmos is magnetized? We know this based on some direct and indirect measure. So for certain atoms and molecules, there's Zeeman effect, so that's a certain splitting due to the magnetic moment, and that splits lines. So this can be directly observed, although it's difficult. There's also synchrotron emission, so Ramil mentioned synchrotron emission. So it's actually kind of a two-part effect. It's due to, Ramil is gone. You're gone right behind the podium. So as he mentioned, there are shocks that propagate. The shocks propagate into the, you're not standing here anymore. Shocks propagate into the interstellar medium. It's kind of a two-part effect. So what do those shocks do? They create cosmic rays, and they will compress magnetic fields. So that's why you preferentially get strong synchrotron emission from from young supernova remnants. But you actually get synchrotron emission from all of the ISM because the cosmic rays get out even beyond the sources, the sites where they are accelerated. So there's synchrotron emission from everything. It all owes to the fact that there are shocks that propagate into the ISM and create those cosmic rays. So that's from particles that are gyrating around, these relativistic particles gyrating around magnetic fields. So we also know that there are magnetic fields from the polarization of dust emission, and that's shown here in two ways. So these are, this is polarized extinction. I think you can kind of see these very faint white little segments. Over here, I think the black is polarized emission, and then these drapery texture is showing the polarization inferred from Planck. So I'll say more about this, but how you infer the field strength. So you can infer field strength directly from Zeeman. You can also indirectly infer field strength from other methods. And typical field strengths are about 10 microgas. So one other thing is, how do we know that grains are not spherical but elongated? We know that because of this polarized emission and polarized extinction. That is, I'll just use this. Marker. Okay, so here's magnetic field. Here's a grain. The grain is rotating, spinning around the magnetic field. So they tend to align with their long axis perpendicular to the grain. And then the emission from grains is parallel to this is a little dipole emitting, so the electric field is parallel to this grain axis. So for emission, the electric vector is perpendicular to the magnetic field. For extinction, that's the same component that gets absorbed out. So the polarized background starlight is parallel to the magnetic field when you're looking at polarized extincted radiation. But we know the fact that it's polarized says that grains are elongated. Okay, so cosmic rays, which I mentioned in talking about synchrotron emission. So this is the spectrum of cosmic rays. There's a lot of different features here, which I won't talk about in detail, but basically it's a power law with some breaks. Below about a GeV, our ability to get information about the spectrum is modulated by the fact the solar wind. These low energy particles actually then are interacting with the magnetic field, and so we're not really seeing directly the unattenuated cosmic ray radiation. So there, to get a better handle on the spectrum, you have to do something else that goes out and is kind of sensitive to the spectrum. And this is from a composite of I think it's all the Gould belt clouds, what the gamma ray spectrum is. So you get gamma rays because the cosmic rays interact with protons, and that interaction produces neutral pions. Those pions decay to produce gamma rays. And so then from the knowing about the interaction cross-sections and the decay rates, the spectrum of the gamma rays you see can then tell you about what the spectrum of the underlying cosmic ray spectrum is. And it's consistent with being dominated by GeV protons. And then there's a turnover at lower energy. So if you take this and then you turn it into a pressure, the cosmic ray pressure is comparable to the other pressures in the ISM, comparable to the thermal and magnetic pressure. And we believe, as I mentioned, that these cosmic rays are accelerated in supernova shocks, and they get about 10% of the supernova energy through the diffusive shock acceleration. Okay, so that was kind of an overview of what there is in the ISM. So now I'd like to talk about some diagnostics in more detail. And so let me start with molecular gas. So what we know about molecular gas largely comes from transitions of the kind of simple molecules, like CO is the most important, but also CS, HCN, these other molecules. A lot of them are at millimeter radio wavelength, so we use radio telescopes to observe them, or my collaborators do. I don't do that. So here are some particularly important, the wavelengths of particularly important species. so ALMA actually is, whereas a lot of the observations used to be at CO 1 to 0, now there's much more observations 2 to 1 because ALMA is a better site, and so you can see this higher frequency transition more easily, and so a lot of the current observations are now in higher frequency in this 2 to 1 line. So then there's a few other lines that are important. So as Ramil mentioned, what are so gas is emitting in these lines. How do you learn what the properties of the gas are? Well, from your radiative transfer class, you'll remember that there's a critical density where collisional de-excitation balances is equal to radiative de-excitation. So that's the critical density, where that's the Einstein A, and that's the coefficient for collisional de-excitation. So that's the so-called critical density. But actually, that's not the only thing that matters. So that's for optically thin radiation. For optically thick conditions, there's what you actually have to account for is the fact that the effective radiative rate is reduced by the fact that photons actually can't escape. So photons, are emitted, but then they get reabsorbed locally. So we use what's called an escape probability to kind of reduce this Einstein A by a factor of 1 minus, this is just an approximation, 1 minus e to the minus tau over tau. So that goes at low optical depth, that goes to 1. At high optical depth, that goes to 1 over tau. But that means that the effective density for where you would see what you can trace with this transition is reduced, can be by a factor of tau, which can be quite large. And in particular for some of these transitions are quite optically thick, and so that means that the effective density that you're tracing is much lower. So, for example, CO, the critical density is about 3,000 for the 1 to 0, or 10 to the 4 for the 2 to the 1. There's actually not that much gas at 10 to the 4 or necessarily even 3,000, but since the optical depth is about 10, that means that the critical density is much reduced. So for example, I guess did I write it here? No, I didn't write it here, but since the optical depth is about 10, the effective critical density for the CO 1 to 0 is about 300. So you're really tracing lower density gas than you would think just naively from the optically thin critical density. And that's also why, things like HCN, you'd say, oh, HCN, that requires a critical density of 10 to the 5. That would be a huge density. So gas like that would collapse very quickly, and you might expect there to be very little of that. In fact, the effective density is much lower than that because it can be because it's optically thick. Okay, so how do we know what the temperature is? From line ratios, if you look at an optically thick species, the line ratios tell you the temperature. And the column density, you can either sort of hope that you've calibrated for optically thin tracers or thick tracers, or you can use optically thin tracers to try to get the total column density. Okay, so molecular gas. So this is the most common tracer for molecular gas is CO. That's because the hydrogen is not directly observable at the densities and temperatures where most molecular gas is found. So it can be observed. So you can see H2 IR emission, but only really in shock-heated regions under particular conditions. So generally, the molecular gas is not observed in H2. CO is optically thick. So that means that if you're looking at the total, if you're integrating under the line, it's not a direct measure of the column density, unlike for atomic gas. So I'll talk more about this, but you use this factor, which is calibrated in different ways to convert from the observed emission to what you think is a total surface density or column density. And that's empirically calibrated, but there are ways to theoretically calibrate it as well. If the beam is not filled, as is often the case if you have a big beam, what you're really doing when you measure the total emission is you're integrating over several clouds. So in that situation, the total CO luminosity is increasing, with a mass of material, basically because you're looking at more clouds, and people talk about that as cloud counting when the beam is not filled, which is often the case. And the beam isn't filled if the temperature, the line temperature, is significantly lower than the temperature that you believe the gas will be at. So if that's much lower, then the beam is not filled. Okay, so one way that the XCO is calibrated is by using extinction and emission. Another way is through gamma rays, but I'll just talk about using extinction and emission of dust. And so this is showing from this is 24 local clouds, and using Planck observations to calibrate XCO. So this is the green here is the average for these clouds. The blue is for Perseus. I think that's from kind of looks like this, I think. So the average over the whole Perseus cloud. This is an average over another cloud, the pipe cloud. And these are, so you can see that, first of all, different clouds have a different relationship. This is not some kind of fundamental relationship between the molecular emission and AV. Varies from cloud to cloud. But there's still an approximate linear relationship at column densities less than, with corresponding to AV less than about 10 or so. And this is for the Orion cloud. Again, you can see this is not a clean relationship. Okay, so you don't think, oh, there's I just take CO and I get the H2 out. It's not, it's the best there is, but it's not a clean one-to-one relationship. But again, you can see there's an average relationship between the total CO emission and AV. And this is the galactic value, kind of typical galactic value for all of these. So this is units because you're multiplying something that's Kelvin kilometers a second by this factor in order to get a column density of hydrogen per square centimeter. Okay, so what's a little bit more of what's happening to, why is XCO at all physically meaningful? Because after all, it's completely optically thick, so it shouldn't be able to give you a linear relationship. Well, what's happening in more detail, so this shows from simulations WCO as a function of the line temperature. So it has this relationship with the line temperature because this is a total width, so you're multiplying a temperature times the width of the line, remembering your radiative transfer. So then here, so why should that know anything about the column density or density? Well, the temperature, the excitation temperature is increasing with density, just in the usual way. Higher density means you're exciting more into the upper state, and so then you'll have more emission from that upper state. So that's what's shown here. Higher line temperature as the density increases. But notice here, the optical depth is really large. Okay, so this is not an optically thin tracer. So that means that the critical density here, from that 1/tau factor, is here at about 300 as opposed to up here at 3,000. So you're turning over not at very high density, but down here because it's optically thick. And then this is the relationship between WCO and density that comes out due to the excitation. And because the density is correlated with column density, then that gives a relationship between WCO and column as shown here. But something to keep in mind is that column versus density this is not a universal relationship. So that's part of why it's different in different clouds is because there's no universal relationship between density and column density. So this depends on environment and the dynamics of the molecular medium. So always if you hear about molecular tracers, take that with caution. For example, I think Ramil mentioned this molecular outflow. I think that they used galactic XCO, which is completely meaningless in talking about an outflow because this reflects the conditions in molecular clouds in galaxies, not molecular gas out in the CGM. So people are not always as careful as they should be in saying how they do this conversions. But this is your caveat emptor. You know, be careful what you buy. Okay, so you can try to calibrate this for galaxies as well, not just kind of on a local scale. So this shows from galaxy simulations and then doing the post-processing radiative transfer how XCO depends on the properties of the galaxy. So you can see that generally you expect XCO to decrease at increasing surface density or increasing WCO. The basic reason for that is that the two things that go into WCO, the excitation temperature and the velocity dispersion, tend to increase at higher surface densities where the star formation rates are higher. So both of those tend to increase for reasons I won't go through into detail, but basically there can be higher turbulence levels at higher star formation rates. Not tremendously higher turbulence levels, but somewhat higher turbulence levels, and that increases this velocity dispersion. It can also affect the excitation temperature. And this is something that can also, you can try to directly calibrate it in observations. This is theory, but you can try to directly calibrate it in observations as well. And it's certainly known that this galactic value of 2 × 10⁻20 cannot possibly hold in regions of very high surface density, because if you used that value, then the total mass of molecular gas would be higher than the dynamical mass of what is the rotation rate. So you know that it has to decrease just empirically. It can't be that large, as Downs and Solomon originally pointed out. Okay, so let's move on to the atomic gas. So as Ramil mentioned, this is observed, it's a great tracer, although it's faint, the 21 centimeter spin flip transition. This has an extremely small splitting, so any temperature is above that splitting. So that means that the relative population in the upper and lower level is just in accordance with quantum degeneracy. The emissivity is proportional to the density. The opacity is inversely proportional to the excitation temperature, which just because of the relative populations and because because the energy is so small. So that means emission is linear in the total column, but absorption, because it varies inversely with the excitation temperature, which basically is measuring the gas temperature with some caveats, is mainly sensitive to the atomic gas. And this is a list of some recent observational surveys of 21 centimeter. Actually, and here's Snezana Stanimirovic was kind enough to provide me, she just made this for a summer school she's doing, and she gave me a copy of this. So this is a nice overview because it tells you, both the resolution, the sensitivity, and the sky coverage of different H1 surveys. And you can see, there are some that have very good coverage, but not so great resolution and moderate sensitivity, and others that have, are not covering much of the sky, but have great resolution and sensitivity. And so this kind of gives you an idea of what there is. These are all emission. So here is kind of an idea of what, when you make these high resolution maps of atomic gas from 21 centimeter, this is what it looks like. So it's beautiful. What you're seeing, though, is you're seeing integrated in velocity, and this is looking at different regions, different ranges in velocity space. So velocity is kind of a tracer of position along the line of sight, but it's not really. So the velocity is, you can very roughly distinguish where gas is based on, where it would be with the galactic rotation curve. But of course, it's turbulent. There are a lot of local velocities. So the velocity is telling you something roughly about where it is. And it's also telling you something about the thermal state. But we don't have any direct distance measurement. We don't have separate measurements of thermal and turbulent contributions to the line width, just from H1 emission. you can, but what you can do is you can say, well, I know an upper limit on the temperature based on the line width. And that's what's shown here from the Hylas and Trollens survey, Arecibo survey. So this is, most of the gas has a line width which is, would put it at corresponding temperature a bit less than 10,000 degrees. So that's the warm medium. And then how do we know about the cold gas? We know about the cold gas by looking at 21 centimeter absorption. From looking at 21 centimeter absorption. So you look at a background source, quasar, and or a bright galaxy, generally a quasar. And then in the on versus, so you look on, you look off, that tells you the brightness temperature on and off. You take the difference between these, and then that allows you to get, since you know the background temperature from looking offline, then that allows you to get the optical depth. But it's actually a profile of the optical depth, as is shown here, as a function of velocity. And the optical depth is inversely proportional to the temperature and proportional to density. That is the excitation temperature here. Whereas the brightness temperature, just from emission, is basically, it's a measure of the total column. So what people talk about as the so-called observed spin temperature is really taking a ratio of the brightness temperature to the optical depth, both of which are directly measured. But it's not actually telling you any particular temperature. It's kind of it's an geometric mean of the actual excitation temperature. So it's, as is shown here. And if you look at the values from these absorption surveys, it puts the temperature at something less than 100 degrees. So that's kind of a reasonable temperature for the cold gas, but it's not the temperature of any one particular cloud. It's basically sensitive to the colder gas. 10,000 degrees you'd never see, both because the lower density, or I should say you can see with these very sensitive surveys, you can actually start to see the warm gas, but that's much more difficult than the cold gas. So you can start to look for lines that have no cold gas. You can actually start to get a measure of the excitation of the warm medium. Okay, so what about the other tracers of the temperature in the warm medium? There are low ionization species, as some examples shown here. And I won't go into the details here, but the typical temperatures of the warm neutral medium based on these, you fit a model to all of these lines together, and that gives you a temperature of around this value. This does not tell you the density directly, so it's really just a measure of the temperature. So what about the pressure, if you actually want to get the density? You can use the ratios of fine structure lines seen in UV absorption. And this is showing an example from Jenkins and Tripp of how this is done. So these are the observations. Then each of these lines is for a different temperature, and then each of the points on the line is a different pressure. So you see where where do you get the best match. And the typical pressure is for the gas that is producing this fine structure absorption is about 3 P over K of about, I didn't write in the units, centimeter per cubic centimeter Kelvin. So you can then combine that pressure with the spin temperature to get this density of typically about 30. Okay, so what about the ionized gas? So what are the tracers of those swarm ionized gas? Well, there's recombination radiation, the Balmer lines. There's also free emission from ionized gas, particularly in H2 regions. There's also radio recombination lines. Both of those are proportional to the so-called emission measure, which is an integral. These all are sort of two-body interactions, so there's a square of the density involved in them. And then you can get particular density diagnostics for lines where the upper level is a doublet, like these oxygen lines or sulfur lines, whereas temperature diagnostics, there are other sets of lines which are better temperature diagnostics. I've written them here. So these are, there's a lot of lore on this nebular emission lines. Osterbrock is kind of the great source on this. You can distinguish the temperature in the warm the diffuse warm ionized medium. This should have been the diffuse ionized gas, because it has, from its line ratios, and you can infer that the temperature is higher. And from the relative strengths of collisionally excited lines compared to recombination lines, you can get the metallicity. So then there's the hot medium, which is observed in soft X-rays from ROSAT and first in ROSAT, but from other missions, and that is giving us a temperature of above about 1 million degrees. The total emission is, again, proportional to the emission measure, and you can look at the strengths in different bands to learn about what the temperature is. UV emission and absorption lines tell you about gas which is somewhat lower temperature, so you can see here these are for different ionization states, some as shown here of, I think this is oxygen, I believe. I think it's oxygen at different ionization states. So, this is kind of the traditional, you'd expect to get, O6 at a certain temperature. But actually, if it's not collisional, if it's not equilibrium, this diagram completely changes. So that's something to, just take with a grain of salt as well, that in equilibrium, the relative populations of those different ionization states is different from if it's undergoing isochoric, that is constant temperature cooling. Okay, so the magnetic field, so one of the ways that the magnetic field strength is inferred is via the Chandrasekhar Fermi method. So there you can think about an Alfvén wave. An Alfvén wave has the velocity perturbations proportional to the perturbations in the Alfvén speed. And those perturbations, since it's just it's a wave, so those perturbations are related to the variation in the polarization angle. So the assumptions that go into this are that the line of sight velocity dispersion is the same as that perturbation in the wave perturbation in the plane of the sky. So you can measure the dispersion and polarization angle, and then measure the line of sight velocity dispersion and infer, treating it as if it's an Alfvén wave, what the magnetic field strength is. And so that's the basic Chandrasekhar Fermi method. And that's within about a factor of 2 compared to, when we test this in simulations. Question?
Yeah, didn't you say earlier, though, don't you have some complications about the different types of dust and if it's polar, like the shape of it?
So, but that's still polarization perpendicular to the magnetic field. One of the things, though, is that you have, if it's not all aligned along the line of sight, if they're not, this all aligned, so the polarization is reduced by, some grains being this way and some grains being this way along the line of sight, and that reduces the dispersion in the angles. So that would tend to make you overestimate the magnetic field strength. So you have to correct for that if you were going to do this. Yeah, good question. Thank you. Okay, so I don't have that much time left, but I'll keep going. So I wanted to turn now to microphysics. And microphysics first of the molecular gas. So first of all, this molecular gas only forms where it's shielded. So this is a reduced chemical network, I should say. So it looks horrible, but it's a reduced network. So this is photodissociation reactions and photoionization. Here, for example, is H2. All of these, you can see, all of these rates are reduced at higher AV. So that's why you need shielding to have, and this for their self-shielding also, I should say, for H2, not just shielding by dust. Green surface reactions are quite important. And if you actually, what determines the kind of rate? There's sort of a minimum time scale for molecule formation, and you can get that just from balancing the formation with dissociation with the green reaction rate. So that's kind of a minimum time scale that you need. So ion molecule reactions are very important as opposed to neutral reactions. I won't go through these reaction networks, but so the ion molecule, and there's a great expert right here. wave to the crowd. Thanks. So for the shielded gas, the cosmic ray ionization and photodissociation is important for the chemistry and also the heating in shielded regions. So where UV is not driving the chemistry and the heating and cooling, the cosmic rays are. Okay, so where do we actually have molecular gas? We can have molecular gas either where both the density and the column density are high enough. So this is for where it's 10%, 50%, and 90% of H2, this is C plus and CO as a function of, this is for a slab model, as a function of column and density. And you can see that you can get H2 actually at moderate density and column, but to get CO, you really have to get above AV of 1. And then this is just showing as a function of column how you make a transition from, say, mostly C plus to CO at large column. So this is from doing chemistry on a large-scale ISM simulation. And again, you can see that so this is showing where there's H2, showing where there is CO. And this is showing WCO as a function of density and as a function of column. So, there is it's observable only at higher AV and higher column. And that's not the same as where the molecular gas is. That's basically the shielding depends on both column and on density, but because you don't need that high column, it largely depends on density, because generally if you have high enough density, there's high enough column because of the self-shielding. Okay, so for the neutral gas, the photoelectric effect is the main thing that's heating the neutral gas, not the molecular gas, but the neutral atomic gas, both the warm and the cold. And so that's what's shown here, photoelectric. In the high AV regions, the cosmic rays are what's doing the heating. And also dissipation of dynamical energy turning it into heat actually starts to be more important in those shielded regions because there's no photoelectric heating. So what's doing the cooling? At low densities or higher temperatures, Lyman alpha is the most important coolant. At kind of intermediate, there's O1 has important fine structure lines, and then C plus is important. So those are, again, fine structure lines, and then the CO is the most important coolant in the shielded gas. And this is just showing as a function of temperature. Okay, so for unshielded gas, that's over here at AV less than 1, the temperature is mainly determined by the UV intensity. So this is kind of solar neighborhood. This is 10 times, that's 100 times. You can see the temperature is correspondingly higher where there's a stronger UV field. But that's really not, when you change the UV field, you've shrunk the region that is molecular. This is the molecular region here. You've shrunk that region, but the temperature is about the same. The temperature in that region in the molecular gas is basically set by the cosmic ray rate because that's what's doing the heating in the shielded gas. So this molecular region, the temperature is determined by the cosmic ray rate. And that's relatively insensitive to the details of the chemistry. This is just showing for fiducial chemistry, or if you just by hand say there's no CO, the temperatures are somewhat different, but really all of those coolants are, still give you temperatures in the same ballpark. So it's really, CO kind of takes over where the C plus and the C1 leave off when they get incorporated into molecules. Okay, so if we want to understand the ISM in a kind of, not just what are the detailed properties here and there, we can start thinking about what is an equilibrium state, or what is the state more generally. So this shows thermal equilibrium. That is the equilibrium function if you balance heating with cooling. So here it's mostly cooling by Lyman alpha. Over here it's mostly cooling by C plus. So this is pressure as a function of density. And there's 3 branches. I'll talk about these a little bit more later. The branch F, branch G, and branch H. And why they have these names I'll get to. It's kind of cute, I think. So this, if you choose a given pressure, so this is the pressure in the solar neighborhood, and that happens to be where you would have both cold gas here, at cold dense gas, and warm diffuse gas. If you take the geometric mean of this maximum warm pressure and minimum cold pressure, that gives you a value which is kind of comparable to that observationally inferred pressure. And then you can think about, well, how would that vary if you look in different regions? After all, this is not the only region. So this is what the cooling function looks like for different radiation field strengths. I guess you can also do this for different metallicities, but this is for different radiation field strengths. This temperature, maximum temperature for the warm medium, is pretty insensitive to that radiation field, and this minimum temperature for the cold is also relatively insensitive. So if you put those together, that says that that pressure that allows you both a warm and a cold medium will depend, these temperatures are just something from microphysics. And so if you kind of say that you have balance between heating and cooling, then you can, do a tiny bit of algebra and say that the pressure should be proportional to the heating rate. So what sets the heating rate? Well, as I said, the heating rate depends on the UV radiation field and also on the abundance of the dust, because you have photoelectric effect on the dust grains. The cooling rate depends on metallicity, because it's mostly, at least on the cold side, it's mostly C+. And so that pressure that you can have both phases really depends on the UV radiation field, which in turn depends on the star formation rate. So if you look at what's the predicted equilibrium curve at different places in the galaxy, that's really just scaling with star formation rate. So the pressure is telling you something about the star formation rate, which is producing the heating. So if we're thinking about the ISM in a generic way, where the pressure is higher, that should be where the star formation rate is higher, and vice versa. And I'll get to that more on Thursday. Okay, so what about the warm ionized gas? So this is for different stellar temperatures. So again, you're balancing heating with cooling. And depending on the stellar spectrum, you can have different temperatures. So basically, you have higher temperatures where the radiation field is harder, because there's more excess energy in the photoions you create than in the recombination, those electrons which recombine. So the relative importance, if you look closely here, so this is a nitrogen line, which is the dominant coolant at this density. If you go to a lower density, instead it's oxygen. So the specific coolants depend on, what the temperature range is and the density range. So, these nebular emission lines, it's not always the same story. So what about the hot gas? So the hot gas is heated by high velocity shocks. So those are generally from supernovae. Stellar winds can also be important, although empirically that's less important than you might expect. This is the cooling function as a function of temperature. So here, this is decomposed into different lines from different metals. So those are the dominant at temperatures less than about 10 million degrees. Then Bremsstrahlung takes over at the very high temperatures. So those are the coolants. So in the last little bit I have, let me turn to global ISM models. And so here, let me start with the kind of first global ISM model, which is the two-phase model of the ISM. And this is based on the concept of thermal instability, which Field first analyzed in the astronomical context. So this is the equations he wrote down and solved for when is there instability. And he categorized two different kinds of instability: the isochoric, that is constant density, and isobaric. And this is for the the cooling function that we now have. At the time, they had a somewhat different cooling heating function. The cooling function was the same. So this is high temperature end, low temperature end. This is above this, the cooling exceeds the heating. Below this, the heating exceeds cooling. So these different branches, this branch over here and this branch over here are stable branches because suppose you are, and this branch is unstable for the following reason. So suppose you're here and you take a step in this direction, then the heating exceeds the cooling, so you'll move back to that point. Whereas if you take the same step here, the cooling exceeds the heating, so you keep going until you get to this branch. So this branch is unstable, whereas these two branches are stable. And so from this, Field considered that since in general, the ISM can separate into two phases. And this is just showing an example from a numerical simulation of that separation into two phases. Oops. Okay, so what's the scale? So this is limited by conduction. And so depending on the conductivity, there's a minimum spatial scale. This minimum spatial scale, if you use a realistic conductivity, is pretty small. So the observed clouds are probably not limited in size by the conductivity, but by the processes that coagulate and disperse these clouds, those turbulent processes. But looking at the time scales here, so that minimum scale is known as the field length. This shows the cooling time scales. So the cooling time in the dense gas at lower temperature is pretty short. It's about 1,000 or 10,000 degrees. It's much higher by it's maybe of order 10 to the 5 or 10 to the 6 in the warm gas. And you can compare to the heating time. So where the sound, I guess that's what's shown here, the sound crossing time. So where that sound crossing time is shorter than the cooling time, you expect to have isobaric, you expect to have that isobaric form of the thermal instability. And indeed, that's what you have in the ISM. So what is this two-phase ISM model? So this was developed by Field, Goldsmith, and Hobbing. So that's the F, that's the G, and that's the H. So Field, George Field was a very warm person. Hobbing, I guess at least they felt that he was a colder person, and Goldsmith, they felt it was unstable. So that's why that's where they were conveniently successive letters of the alphabet. So as I mentioned, there's they at the time they had these same different coolants. At the time they thought that the cosmic rays were actually the main heating. We don't think that anymore because we see these PA features, and so we think that PA, the photoelectric heating from small grains, is more important for heating these phases of the ISM. So the main point is that they said, well, there's two stable phases, and what was previously thought to be this G phase was thought to be the main. This is from their paper. This new phase, previously unknown, is what they concluded should fill much of the volume of the ISM, and that's still what we think today. And they also suggested there should be a hot phase. This is not well known that was in this paper, but that was in this paper as well. Okay, and so they also argued that there should be different phases at every height, not at the highest heights because the pressure is too low, but at most heights within the galaxy. Okay, but there's actually a third phase, and the reason there's a third phase is because of supernovae. And supernovae, as shown here in this simulation, drive blast waves into the surrounding interstellar medium. Those blast waves, you can see the high temperature here in the center. That's from shock heating. And this is make me crazy if it keeps playing. So these are the classical evolution phases of a supernova remnant. If you actually do this in detail with a simulation, you find that there's this phase of the pressure-driven snowplow does not actually live very long, basically because the material kind of, instead of having this adiabatic hot gas in the interior of the supernova remnant, actually that gas tends to condense onto the inside of the leading shell, so you lose the hot gas, it cools away. And so the duration of the pressure-driven snowplow actually is not that significant. And what that means is that the momentum, which does not increase that much after shell formation. So there's a shell formation time which depends on density. I'll talk more about this in my feedback lecture, but the momentum increases by about 50% after shell formation. And you can also look here at the hot gas mass. So that increases as more and more gas is inside the shock, but after shell formation, that drops. And that's basically because material is cooling out. But still, the low density interior, if we look at this late time, the low density interior stays hot. So basically, the hot stuff is the stuff that's at density that's at too low to cool. Okay, so last few minutes, I'll say a bit about the three-phase interstellar medium. So ideas about this kind of started actually with Spitzer, the hero of the interstellar medium, in the late 50s. And he actually postulated that there has to be hot coronal gas because what he suggested is that since there were clouds observed in calcium absorption lines towards O stars that were very far away, like 500 parsecs away, so he inferred that there must be some high pressure medium that could confine those clouds because otherwise they couldn't be at density high enough that there could be these absorption lines. So then Cox and Smith suggested from the supernova rate being high, they suggested that actually there would be a lot of hot gas, and they suggested a network of interconnecting tunnels of this hot gas within this, what was then thought to be just a warm-cold ISM. McKee and Ostriker suggested that, in fact, the hot phase fills most of the volume in the ISM, and they focused on they were focusing on warm, cold clouds that are created by supernova compression and then destroyed by conduction and evaporation. And just a comment from the McCrae and Snow review that basically they point out here this point I mentioned before, that the characteristic temperatures are really set by atomic or more generally atomic and ionic and molecular properties of the gas. Okay, and here's just from the McKee-Ostriker paper. So that's not me, by the way. Different Ostriker. I was born, but this isn't my paper. So this is kind of a close-up of. So this is not really consistent with our current model. We don't kind of think that all of the ionized gas is just in these layers around the neutral clouds, but this is their concept at the time. And what went into the model, so they had observational inputs to this model, which were, they were motivated by the solar neighborhood. So they took the supernova rate, which will be related to the star formation rate divided by, this was per unit volume. They also took as an input the mean density, which was a kind of empirical input. And they also took as an input the UV radiation intensity. So all of those that they took as inputs to their model. But of course, if you want a fully self-consistent model of the ISM, those should not be inputs. You need a self-consistent theory. And so to have a self-consistent theory, you have to understand, what star formation rate should you get to be self-consistent with this density, and what UV rate should also be self-consistent. So you want all of these to be self-consistent quantities. So to have a fully self-consistent ISM, and I'll talk more about that on Thursday. So basically, you want the ISM conditions and star formation rate to be self-consistent, and you can kind of put a number of equations together to say you're balancing heating with cooling, turbulent driving with dissipation, and also you have force balance of the weight of the ISM has to match the pressure. So I'll talk more about that on Thursday. That will be lecture 3. And finally, I have 0 time left, but I'll just say there's a lot of, but this is my last slide. So I didn't time this at all. So we'll go into lunch for your questions. Or you could ask me questions at lunch. So there are a lot of modern studies of the three-phase ISM. Many people here are working on these issues in detail. I think I should show restraint and not go through these, but you'll see some names here that are familiar. Mordecai is here, other people are here. So these are some of the current questions that people are very interested in. Simulations are clearly very important for this because that's how we can actually get very detailed models. There's a lot that's still not understood because this is an active area, but it's very exciting. And again, I'll emphasize that if you don't understand the ISM, there's no way you can understand galaxy formation. So take advantage of the experts who are here, learn about the ISM, and come talk to me.
Thanks, Eve. So we have time for a few questions. Josh. Yeah.
So you said that we no longer think that the clouds are kind of like these round structures, and then there's, the cold neutral medium inside the warm neutral medium. So what do you mean? What's kind of deviated from that model?
Well, that sort of shell structure where you have ionized and then warm and then cold. Certainly, we do think that the cold clouds are within the warm medium, but it's not necessarily a shell-like structure. I mean, to the extent that, the ISM is a PDR, so that's a photo dissociation region. So, the whole ISM is a PDR, but with a lot of different conditions. So we don't think the clouds are round because they're always being shaken up and destroyed by, stretched out by turbulence, put together. So we don't think that they're individual round clouds. We also don't think that the hot ISM is basically volume filling. It's filling about half of the volume of the ISM. But yeah, there are many aspects of it that we still believe today, but just not in that specific detail.
Other questions?
Hey, everyone needs lunch.
Laura.
I'm trying to use this and it says red. I did.
Yeah,
Red is fine? Okay. So Romil showed us that the accretion happens through these filaments. Is that any important source of turbulence?
So it could be. I mean, this is, if you look at, it's not, so that will since it's high angular momentum, it will preferentially land in the outer parts of the galaxies, so that may stir up turbulence in the outer parts of galaxies preferentially. But the accretion rate is not very high, at present day. Of course, we're not only interested in present day ISM, we're interested in ISM at all stages, so it can be important in stirring up turbulence. But I think the thing to keep in mind when thinking about that is that the dissipation time is always set by the scale height. So, however you're driving it, it dissipates very quickly. So, whatever the driving process is.
Corey.
So, when talking about polarization from dust, either emission or absorption, you talked multiple times about how the dust is aligned perpendicular to the magnetic fields.
In an average, I should say, it doesn't have to be perfectly aligned, but it's spinning so fast that the average cross section. So even if it's sort of, I'll get this back. So even if it's like this, the average cross section is still perpendicular.
Okay, and so what is the evidence to show that the dust does align?
So the fact that there's polarization. So if there were there were no polarization, there wouldn't be polarization if there were no alignment.
Right. Okay.
It would if the grains had random angle. Well, that it tells you both that they're that they're not spherical and that there is alignment, because if if they were spherical, there'd be no polarization.
Right.
If they weren't aligned, there would it would all average out. So
right.
yeah.
Okay. Thanks.
Why don't, what time is it? All right, it's 1:01, so let's break for lunch. Eve is around, well, for 5 weeks, 6 weeks.
Right,
So feel free to ask your questions. Otherwise, let's thank both Eve and Ramil.